Welcome to this session. In this video, we cover simple, pure, and general shear and the relationship between stress fields and ductile shear zones. The formation of foliations and shear sense indicators in simple, pure, and general shear mode can be understood if we understand the effects of angular relationships between stress fields and shear zones. And in an ideal case, in rocks that are mechanically isotropic, structures of deformation should always be controlled in their orientation by the orientation of the stress field, and they should form in orientations that correspond to the stress vectors, particularly to the orientation of sigma 1 and sigma 3. Here we see an example of such relationships between sigma 1, the largest principal stress vector, sigma 2, and sigma 3, the smallest one, and various structures of brittle and semi-brittle deformation structures. We see, for instance, mode 1 joints or tension gashes would form parallel to sigma 1 and sigma 2 and perpendicular to sigma 3. Stylolites, which are common in marbles, they are dissolution fronts. They should form perpendicular to sigma 1. And echelon tension gashes have their specific relationship with the stress field. And also faults form in specific orientations with respect to the stress field. We have seen that in Anderson's fault theory that predicts that conjugated faults always form at 30 degrees with respect to sigma 1 and with 60 degrees with respect to sigma 3. And the intersection line between conjugated fault planes would be along sigma 2. However, that is not always the case. Ductile shear zones and also faults do not always form where they should at 30 degrees or 45 degrees with respect to sigma 1, depending on whether we are talking about the brittle field or the ductile field. Why is that so? There are various reasons that can change these orientations. One is the activation of pre-existing mechanically weak zones that can be layers in layered rocks that have a low shear strength, rheological contacts along of which stress concentrations are common, or older pre-existing shear or fault zones that are in an orientation that makes them favorable for reactivation. Furthermore, there could be a rotation of shear zones in a fixed stress field. So shear zones are strain markers, are features that can rotate during progressive deformation and then move out of the favorable orientation of 45 degrees with sigma 1. Similarly, we could have changes in the regional stress field orientation during progressive deformation, and an existing shear zone would remain in an orientation while the principal stress vectors change their orientation. Accordingly, we need to notice that the geometric relationship between stress field orientations and slip surface is an important matter in structural geology and in the kinematic analysis of rocks and regions. Let's discuss simple, pure, and general shear, which describe, as we will see, the geometric relationship between stress field and shear zone orientation. Here first, simple shear, a shear zone oriented, as we see, which has a specific relationship between the principal stress vectors and the shear zone orientation. This is an ideal case. 45 degrees exists between the sigma 1 stress vectors we see here and the shear zone surface. Perpendicular to sigma 1, we would find sigma 3. Sigma 2 would be in the viewing direction perpendicular to the surface that we are looking at. This orientation is also the orientation in which the maximum shear stress can be resolved along the shear planes that we see. The displacement would take place along foliation planes, and we would have in this example here a top to the right movement of deformation. Progressive deformation would shear a reference rectangle that we see here outlined in a red dashed line into a rhombic shape with a top to the right kinematic movement. This is the mechanically ideal configuration. This is how ductile shear zones would form in a mechanically isotropic rock, for instance in a unfoliated, unlayered plutonic rock that is hot enough to allow ductile flow. In pure shear, the configuration is different. Pure shear is defined by a stress field orientation that is perpendicular to the shear zone boundaries with its maximum principal stress vector sigma 1 and parallel to the shear zone with its minimum principal stress sigma 3. Also sigma 2 would be parallel to the shear zone. The rectangle that we see here, our reference body, would be shortened parallel to sigma 1, and it would extend parallel to the minimum principal compressive stress sigma 3. That does not mean that the shear zone would become narrower with progressive strain because more and more rock would progressively be affected by shearing, and therefore shear zones would rather increase in thickness during ongoing strain. This is not the orientation of maximum shear stress, which, as we have seen, is 45 degrees with respect to sigma 1. Then we have the situation of general shear. In general shear, the orientation of sigma 1 with respect to the shear zone is neither 45 nor 90 degrees. We see here this angle is somewhat larger than 45 degrees, and we see perpendicular to it sigma 3 is neither perpendicular nor at 45 degrees to the shear zone as well. The reference body that we have outlined here in dashed lines would be deformed into a rhombic shape, but in contrast to the simple shear case, we also would have a component of vertical shortening. So this is a combination between pure shear and simple shear. Let's consider a fieldwork example, a curving shear zone that is formed in a stress field of constant orientation. We see here the stress field orientation with sigma 1 acting from top left to bottom right, obviously opposed by a stress vector of equal magnitude. The same for sigma 3 acting from top right to bottom left and vice versa. And here we see a shear zone that changes its orientation from left to right, perhaps because it is deflected around some sort of plutonic rock that is not easy to shear and around of which this shear zone we see a wrapping of that shear zone around this highly competent body. When we now look at different areas in this shear zone, we would see here on the left-hand side the shear zone would be a simple shear zone, because here we have a 45 degrees angle between the shear zone boundary and sigma 1 and also sigma 3. If we approach the bend in the shear zone boundaries are no longer in the simple shear orientation, but they are also not perpendicular to sigma 1. In this part of the shear zone, the deformation would be accommodated by general shear. In this part of the shear zone, we find that the shear zone boundaries are now perpendicular to sigma 1 and parallel to sigma 3. This part of the shear zone would be exposed to pure shear deformation. Everywhere except in the pure shear part of the shear zone, we would have a simple shear component that indicates dextral movement. If we assume that this is a map view, then we are dealing here with a steeply oriented shear zone. Here we would have dextral strike slip. Here we would have dextral strike slip combined with a shortening perpendicular to the shear zone. Here we would find pure shear without a uniform simple shear component. On the last slide, we have seen wherever there was a simple shear component, it was dextral. However, if the shear zone would be oriented in this way, here in the left example, the simple shear zone, because of the 45 degrees with respect to sigma 1, would be sinistral. Also in this example, we would have a sinistral component of simple shear, but since this shear zone is not oriented at 45 degrees with respect to sigma 1, we are looking at a general shear zone with a simple shear component that is sinistral. Reversed sense of shear also applies to conjugated shear zones. If we look here at a set of ductile shear zones, one vertical, one horizontal, with a stress field as indicated, we would find that the horizontal shear zone is a dextral simple shear zone, whereas the vertical one is a sinistral simple shear zone. That is the very essence of conjugated shear zones. These two sets are forming in the same stress field, but in orientations that require opposite sense of shear. Obviously, that also works in the brittle field. I again remind you of Anderson's fold theory. In the brittle field, conjugated fold planes would form at an interface angle of 60 degrees, which corresponds to 30 degrees between the fold and sigma 1. And also here, we observe opposite senses of shear along these conjugated folds. So in summary, we see the generation of pure shear, simple shear, or general shear zones depends entirely on the shear zone orientation with respect to the prevailing stress field. Simple and pure shear flow require very specific geometric relationships between the stress field and the shear zone orientation. And so statistically, we would say they are less common in nature than general shear zones, which can be in an orientation anywhere between 45 degrees with respect to sigma 1 and 90 degrees with respect to sigma 1. Pure, simple, or general shear flow is not instantly obvious from field observations. If you do field work and you come across shear zones, it is not easy or obvious to decide whether a shear zone has formed from pure, simple, or general shear mode. Paleo stress field analysis is difficult but can be done, and that would provide evidence of the orientation of the paleo stress field under which the ductile shear zone may have formed. We also can do that from the statistical analysis of shear sense indicators, which is not so tricky. We will see that on the next few slides, but which requires the presence of a large number of well-exposed shear sense indicators that we can evaluate in a statistically meaningful way. Let's have a look how that works. In order to understand the importance of shear sense indicators and what they indicate, let's have a look at the three cases: pure shear, simple shear, and general shear in terms of continuum mechanics, and we will see how that works, hopefully from the examples that you will see on the next few slides. So pure shear, we were saying, implies shortening perpendicular to the shear zone and stretching parallel to the shear zone, as indicated here from our reference square to our post-kinematic final product. So here we see a series of sketches of a reference circle that during progressive deformation deforms to a strain ellipse, and various markers that rotate and multiply during this progressive accumulation of strain. So let's assume at the beginning of deformation we initiate conjugated shear zones in our rock that right at the start can be considered as undeformed. In a pure shear situation, as indicated here on the top right, we would shorten vertically and stretch horizontally, and accordingly conjugated micro shear zones would form in the way as indicated, with a top to the right shear zone from top left to bottom right, and a top to the left shear zone from the top right to the bottom left. These shear zones with progressive vertical shortening and lateral stretching would start to rotate, and here in the next stage we can see that these shear zones with opposite sense of shear have started rotating towards a horizontal line that we call the fabric attractor. At the same time, new micro shear zones are developing in the orientation of maximum shear stress, which is at 45 degrees with sigma 1, which in our example here is vertical. In the third stage, the red shear zones, the first ones, are already approaching the fabric attractor. Also, the second generation of shear zones has rotated, and a third generation of micro shear zones is forming in the orientation of maximum shear stress, just as the two previous generations of shear zones. We also can see that the shear sense along the shear zones remains always the same. The shear zones that form in the upper right to lower left quadrant always remain top to the left, whereas the opposite shear sense is seen in the other shear zone. That would imply that all shear sense indicators that form during progressive strain are either top to the right or top to the left, in dependence on where they form and in which orientation they form. All marker lines or micro shear zones, minerals, whatever is oriented in this rock in a specific orientation, will progressively rotate towards the fabric attractor, and with progressive strain, vertical shortening will become more and more intense and will be compensated by lateral stretching. This is a way how we can form effective foliations, because if all our marker lines, all our micro shear zones rotate towards the fabric attractor, this will also be done by all other strain markers, such as mica grains, for instance, or flattened quartz lenses. This will end up in a pronounced, strong, possibly continuous foliation in the rock. We can make some further observations in the pure shear case. Let's assume there is a strain marker that at the beginning of the deformation is already parallel to the fabric attractor. Let's say there are some mica crystals present in the rock that are oriented horizontally. With progressive strain, they would not have any reason to rotate either clockwise or anti-clockwise. They are already in the preferred orientation of the fabric attractor, and that means such a strain marker would remain where it is in the horizontal orientation. The same would apply to a strain marker that happens to be vertical. If we have any kind of strain marker that is in such an orientation, it would not rotate, it would shorten vertically and perhaps stretch horizontally, or depending on the mechanics of the strain marker, we might find symmetric folds forming. We have discussed similar features in chapter 10 of this lecture series. But what is important is that all other markers that are neither parallel to the fabric attractor nor perpendicular to it will rotate either clockwise or anti-clockwise towards the fabric attractor, and that will form shear sense indicators of opposite sense of shear depending on the quadrant in which these strain markers are oriented. No marker remains in the orientation of maximum shear stress for a long time. That is an important feature of pure shear. We see here whenever we form any strain markers in this orientation, very quickly with progressive vertical shortening and lateral stretching, these strain markers will rotate out of this favorable orientation of maximum shear stress. Eventually, a foliation will form parallel to the fabric attractor, and that most typically will be a continuous foliation. Let's consider the simple shear sense. Here we now have a different configuration between shear zone orientation and the stress field. As indicated here, the shear zone boundary is at 45 degrees with respect to sigma 1 and sigma 3. And again, we will form at the beginning of deformation a set of conjugated micro shear zones with opposite sense of shear. And we see here this would be a vertical shear zone and a horizontal shear zone at 45 degrees with respect to the principal stress vectors. The vertical one would have a top to the left and the horizontal one a top to the right sense of shear if the stress field is oriented as indicated. We have labeled these micro shear zones here S and C, and if you have watched the video on shear sense indicators, you will obviously notice that this section here explains how SC fabrics will form during progressive strain. What we see in the first stage of progressive strain is that the S-plane starts to rotate. It rotates clockwise in our example, so if sigma 1 is acting from the top left and bottom right onto the shear zone, the S-plane rotates in a clockwise sense and for some time maintains its top to the left sense of shear. The C-plane does not rotate because the C-plane is already in the orientation of the fabric attractor, which is the shear zone boundary. We continuously will form new micro shear zones in the orientation of maximum shear stress, which means in this case vertical and horizontal. Progressive strain will make our reference circle more and more elliptical, and accordingly our strain ellipse is becoming narrower and longer. A third set of micro shear zones is forming, indicated in green color. A vertical one here now looks very short in this sketch with a top to the left sense of shear and a new one overprinting the previous red and blue shear zones parallel to the C-plane. The C-plane remains in the orientation of maximum shear stress. It does not rotate as we see, and it also maintains its top to the right sense of shear. What we can see here is that the S-planes, which are rotating further and further to the right, change their sense of shear from top to the left to top to the right, because at some stage they are rotating through the orientation of sigma 3, which is perpendicular to sigma 1. And as soon as the micro shear zones have crossed this orientation, they are in an orientation where top to the right sense of shear is forced by the orientation of sigma 1, which now acts obliquely to them, forcing a top to the right displacement. In the orientation of the C-plane, we maintain the maximum shear stress, and that promotes very effective dissolution creep. If dissolution creep is strongest along the C-plane, we will remove most of the quartz along this orientation, and that will relatively enrich insoluble or less soluble mineral phases such as mica. And from the removal of quartz, a mineral phase that is easy to dissolve, and the concentration of micas, we will produce a pronounced foliation parallel to the C-plane. The S-plane, as we see here, rotates quickly out of the orientation of maximum shear stress. That means that along the S-planes, dissolution creep will be less effective. And therefore, the S-plane in SC fabrics is always less prominently developed. During progressive strain, the rotation velocity slows down, and that in many cases leads to a situation where we have intensely developed C-planes and S-planes that remain obliquely oriented with respect to the C-plane. That is what we can use as a shear sense indicator in SC fabrics. And if you want to know more about SC fabrics, please have a look at the video on shear sense indicators. I want to mention again, it is important and characteristic for simple shear flow that along the S-planes during progressive rotation and progressive strain, the shear sense changes from a conjugated shear sense that is opposite to that along the C-plane into a synthetic shear sense, a shear sense that is the same as we see along the C-plane. Let's have a look at a diagram that pretty much shows the same that we have seen, but let's now apply it to a rock with a random orientation of strain markers at the beginning of deformation. Again, here a simple shear zone. The stress field orientation is the same as we have seen on the last slide. And let's assume we have randomly oriented strain markers such as feldspars in a isotropic unfoliated granite, represented by these orange rectangles that we see here. As soon as simple shear starts to affect the rock, we will see that all of these strain markers rotate in a clockwise sense and start to accumulate in an orientation that is pretty much parallel to the long axis of the strain ellipse. And if these feldspar phenocrysts develop shear sense indicators such as sigma clasts, all of them would indicate a top to the right sense of shear. So simple shear is characterized by a uniform rotation sense and uniform shear sense indicators, all indicating the same sense of shear. This is not so in pure shear. If we go back to our example from pure shear, where we accumulate progressive strain by vertical shortening and lateral stretching, our randomly oriented strain markers would rotate equally in clockwise and anti-clockwise orientation, depending on their orientation at the beginning of deformation. We see here those with their long axis in the gray quadrants, they would rotate in an anti-clockwise rotation sense towards the fabric attractor, whereas strain markers oriented in the white quadrants would rotate in a clockwise sense towards the fabric attractor. Markers that are vertically or horizontally oriented might not rotate at all. They might stay in the fabric attractor if they are horizontal, or they might get shortened if they are vertical, or perhaps even folded or broken up. The statistical evaluation of shear sense indicators in a pure shear zone would show an equal distribution of top to the right and top to the left shear sense indicators. Accordingly, if you are involved in kinematic analysis of ductile shear zones, you might very well come across shear zones in which shear sense indicators show the opposite sense of shear. Such an observation can be explained by the presence of a pure shear mode or a pure shear component in general shear, as we will see on the next slide. In the general shear case that we see here at the bottom, we see a combination of simple shear and pure shear. And comparing the orientation of the stress fields for the three cases, we see here a 45-degree angle between the shear zone boundary and the principal stress vectors. Here the principal stress vectors are vertical and parallel with respect to the shear zone boundary, and in general shear they are somewhere in between these two end-member orientations. So in general shear, again, we will have different quadrants in which strain markers rotate in opposite directions, only that the quadrants are no longer equal in size, as we have observed in the pure shear case. In this situation here, for instance, we will find a minority of strain markers oriented in such a way that they will rotate counterclockwise towards the fabric attractor and accordingly develop top to the left shear sense indicators. The majority of strain markers will rotate in a clockwise sense towards the fabric attractor, and accordingly they will produce a top to the right shear sense indicator such as sigma clasts or delta clasts. With progressive strain, all our shear sense indicators will rotate more and more towards the fabric attractor, and if a strain is very large, they eventually will form phi clasts and will become unusable as shear sense indicator. If we have here a case that consists of 50% pure shear and 50% simple shear, we will get a distribution of shear sense indicators of 75% top to the right and 25% top to the left. So why is that not 50-50? Well, 50-50 it would be in the case of pure shear. So, and if you combine simple shear, in which all shear sense indicators are pointing in one direction, and a pure shear case in which you have a 50-50 distribution, you will end up with a 75 and 25 shear sense indicator distribution, top to the right and top to the left, if the components of simple shear and pure shear are equally strong. So what can we learn from that in summary? First, the statistical analysis of shear sense indicators in ductile shear zones allows to estimate the proportion of simple and pure shear. This is not always very accurate. It depends on the number of shear sense indicators that we can observe. And the more we have, the more reliable our evaluation and interpretation will become. It is therefore very useful to examine very carefully the macro and micro fabrics, the foliation and the lineation orientations, of course, all kinematic indicators, all kinematic observations that may or may not indicate tectonic overprints. It is very important that in a given shear zone that we want to analyze for the purpose of estimating the proportion of simple and pure shear, that we can exclude tectonic reactivations and overprints in such shear zones, because if our shear zone has a very complex history with, for instance, changing stress field orientations, then the method of evaluating shear sense indicators will not yield a useful result. The amount of strain or the shape of the strain ellipse or the ellipsoid does not allow us to interpret the proportions of pure shear or simple shear flow. we could have exactly the same shape of a strain ellipse or ellipsoid produced by pure shear, by simple shear, or by general shear. So the amount of strain and the shape of the strain ellipsoid in itself is inconclusive with regard to the mode of strain, simple, pure, or general shear, that has caused the deformation. If we are dealing with complex shear zone histories with changing proportions of pure shear and simple shear, the interpretation usually becomes very difficult, but such shear zones are, of course, possible in complex orogenic settings. I believe that was all I wanted to tell you about the nature of pure shear, simple, and general shear. Thank you very much.